So I'm honored to be invited to present the work that we've been doing with definitely the help of Amazon, and it has been throughout the past 4 years an amazing journey, and it's more of this journey that I'll be explaining of how we started to use the cloud into production environment. And this wouldn't have been possible with the help of great people at Amazon Web Service, as Angel, Cam, and Leo at the beginning, and then with Todd, Nick, James, and now Chris Noonan, that have been extremely helpful to make this possible. Otherwise, this wouldn't have been definitely possible. So my presentation is on purpose. I only have 30 slides, and so we have 50 minutes. So I wanted to be extremely interactive. If you have any questions, please don't wait the end. Raise your hand, you'll have a microphone, and ask the question straight away. So because it's the purpose is really to gain insight of how we managed to do it, so you can do it yourself. That's the key point. And it's not that complex to be able to leverage the great infrastructure that is made available to us. So something that so the first part of my presentation is to explain what do we mean by precision medicine, where President Obama, when he announced a few years ago how the whole concept of precision medicine is to make sure that the right drug could work for the right patient. What do we mean by this? You all look at your pharmacy, you all have in a pharmacy cabinet, you have incredible amount of drugs. How on earth do you think they can work on so many people at the same time? And so we all know that some drugs won't work for some individuals, but we don't know before taking it. So this whole concept of, and you all heard about it, precision medicine, what does it mean? It means to know which medicine, which drug is going to work for which patient, even before taking it. That's the key point, so that you don't lose time. And to use many different sources of knowledge and to aggregate everything in order to discover this. So talking and the best way to explain precision medicine, and that's what I showed to my students at Harvard, is what this whole concept didn't started 2 years ago. It started hundreds and hundreds of years ago. How do you think that a diagnosis of leukemia was done in the 18th century? It was considered as being a dysregulation of the 4 humorisms: phlegmatic, choleric, melancholic, and sanguine. So the diagnosis wasn't wrong. It was incredibly imprecise. And because it was imprecise, of saying that potentially a leukemia was a deregulation of the sanguine humorism, the treatment was completely wrong, where the treatment was bloodletting. Bloodletting won't help someone with a leukemia. So the key point is the diagnosis wasn't wrong. The diagnosis was so imprecise, then this wasn't leading to having the right treatment. Because the key point is where you had at the beginning something that was disruptive in the sanguine humorism, where 50 years ago there were more than 5 or 4 main categories of leukemia: acute, chronic, myeloblastic, lymphoblastic leukemia. Today there's more than 400 different subtypes of leukemia. Why? Because we have now very precise diagnosis. And why is it important to get a name of each subtype? Because having the diagnosis, having the true name of the disease enables to get the prognostic. Is this something that is life-threatening or not? And having a potential treatment. You can't have a treatment if you don't have the correct diagnosis. So the key point is really, and that's what we mean by precision medicine, is finding all those various subtypes. But in order to do this, because at the end, every single patient is like a rare disease, because everyone is unique. And so the key point is really to be able to find all those different subtypes by aggregating all the data together. One of the best examples of precision medicine made the front page of the New York Times. Why? Because it was even before having the disease, so that's even better. Where because of multiple points, where Angelina Jolie had a very strong family history of breast cancer, And because the genetic testing was telling her that she had this mutation that was transmitted to her, so the key point is the association of both. If there wasn't the family history, this wouldn't help. It's really the family history plus the genetic testing. Then she had a very high risk of more than 88% of developing a cancer herself. So then, as a discussion with a doctor, she then decided of doing the double mastectomy in prevention of getting the cancer. Does this, her case of breast cancer, represent all cases of breast cancer? No, this is only 3% of cases of breast cancer. It's a very unique, it's going down the tree very, very precisely, where it's even better because you can have a treatment before getting the disease, because you know that it's going to appear. So that's the key point of trying to go down this tree. And then, now on the other side, where are we in the context of the opposite, with autism? 1 boy out of 54 has autism. 1 child out of 84 has autism. And so, where are we in finding those subtypes? Why don't we have today any treatment for autism? Because we haven't found any subtypes yet. We are exactly like leukemia and bloodletting 200 years ago. We haven't found any subtype yet, so that's why, because you don't have the subtypes, you can't find a potential treatment, because it would be like saying someone has cancer. Well, which cancer? Which is a subtype. So it's really the question of bringing down and understanding which are the various subtypes. And so how to achieve this now? Now that the problem of precision medicine, now what is one of the solutions that can enable to resolve this? Is bring everything together. Taking the analogy of Google Map, we all have on our iPhone in production Google Map with all the different layers of information, where you have the satellite, postal code, opening and closing hours of the different shops. Why can't we do the same with health data? Why can't we have everything into one central place, not centered by GPS coordinates, but centered by the patient identifiers across all the different layers of information that we have around our patients into one central place that will enable us to find the subtypes, because we need multiple factors of information to be able to find all the different subgroups. And so all these pancakes, and I'll show you examples of how, using the leverage of the scalability of Amazon Web Service, where we were able to create this for real. And one of the examples is in the context of many of the various infrastructure that we created, is to be able to take all the phenotypic data coming from the hospital, coming from the clinical trial research cohort, or the example here of the biobank at Boston Children's Hospital, where we integrated all the biobank samples, all the patient consent. The patient consent at the end is another phenotype, another clinical data, which is at the end is the most important one. That's the most crucial one in order what is in the patient or in the parent's mind in the context of data sharing. So we consider the patient consent as one of the phenotype linked to all the genomic data around those patients into these layers of pancakes of creating those patient-centric information commons. And that's where we developed open source tools like I2B2 Transmart to enable this. And then once you have all the data into one space, the purpose of what we are trying to do, and in my lab where I have half of my team as software developers and half as postdocs, is not to create yet another nice database that even could be on Amazon, and everything is on Amazon, but it's not the question of, the end goal is not to have a database. The end goal is that this database is useful now and not tomorrow, to make sure that we can use it for research and being impactful and finding the subtype of disease. So then we create a different access to this database, the very nice user interface, and I'll show you a quick live demo to show you how this looks like, but then to be able to do also high throughput analysis directly on the database, to be able to do genome-wide association study or phenome-wide association study, but to make sure that this is useful right now. Taking the example, I'll show you a different project like the ENHANCE National Health and Nutrition Examination Survey. And since 1960, they have been collecting with different tracks across the US all different measurements of not patients, but participants, where there's more than 1,300 measurements for 41,000 patients. So this is real patient data, but this is open data. This is publicly available data that was gathered from 300 Excel sheets on the CDC website and aggregated it to one central place so that you can query and use it straight away. And this enables, as being one of the gold standard for exposure and behavior data, for the context of drug development, infectious agent, and about the exposition with different pollutants. So what I want to show you is a very quick live demo of the system. And that's my 3 kids. So Enhance, everyone can go on the website, enhance.hms.harvard.edu. This is totally publicly available. So there's no authentication, no authorization to access the system. I just wanted to show you a concrete example of what I meant of creating this patient-centric information common, where we integrated into one central place all the demographics, examination, laboratory, and questionnaire around those patients. So for example, if I want to look at all the patients, males, then generate summary statistics. So all this is running on a HIPAA-compliant Amazon cloud. And I'll show you afterwards how we created this. But first, I wanted to give you an example so you have in mind what I'm talking about. So for example, out of the 20,000 males, description of the age and race of the various individuals. And so now if I want to compare male versus females between the cohorts, I have this tool that enables me to generate hypotheses, to be able to compare between the various groups, of making comparison between any point of layers in the data set. And this can be clinical data, environmental data, or genomic data. So for example, if I go into the examination, blood survey, and the mean diastolic blood pressure. You have the diastolic and the systolic blood pressure. The most important one is the diastolic one. And so if I take the diastolic blood pressure, drag and drop, you'll see automatically a 101 statistics showing you how you're comparing the blood pressure between male and female. And you can see that for male, 65 versus 64 for female, and the result is significant at the 95% confidence interval. So you have a higher blood pressure for male than female. That's it. That's what I wanted to show you. That ends my live demo. This is just showing you an example of what I meant, so you can switch back to the slides, of creating this patient-centric information common, where I put together the demographic lab data, the examination data, everything into one central place. So you can go and play with it directly, the enhance.hms.harvard.edu website. Another example of also open data, where we integrated multiple research cohorts together from the context of the NCATS, NIH National Center for Advanced International Science, of the Global Rare Disease Patient Registry, where we integrated into one central place multiple registries of very rare patients into one central point. And this enables to be able to do analysis across all those different registries. So this is also open data. You need to register, authenticate and register, and 10 seconds later, you can have access to all the data to do research. A third project is the UDN, Under-Diagnosis Network project, where patients that haven't been diagnosed come and go onto the website to be able to have deep phenotyping and in contact with all the healthcare provider to be able to have all genome and all the exome that has been in order to potentially find a diagnosis. And there has been more than 200 cases that have been solved using this project, running into a HIPAA compliant and FISMA moderate compliant Amazon cloud, whereby putting all the clinical and the genomic data together. And so the key is really how to put together all those different layers, and then, as it was presented also this morning, is to be able to, the NIH wants to create open source research infrastructure so that investigators can have much easier access to all the clinical and all the genomic data. So this is one of the examples of the Data Commons project, where we are using this infrastructure to make this data available to many different investigators into a much more scalable and research environment, using the clinical data and using the health variant store to be able to have something much more scalable and running onto Amazon. And so one of the key points of the success is to make sure to create and to respect the HIPAA law. So the HIPAA is a Federal Health Insurance Portability and Accountability Act, and the goal is to raise the level of security. I work at Harvard Medical School. It's a university. It is not a covered entity. So the first reaction of Harvard lawyers was, why on hell do you want to be HIPAA compliant where you don't have to? And my answer was, why not? Because this was just a level of attainable, reachable level of security that we could do it. And everything started when we, with a discussion with Cam Watt from Amazon in my office 4 years ago, and showing all the various projects where we were on a very rare disease, Phelan-McDermid syndrome. We were looking at processing all the clinical notes of those patients that we were sent about the participants in order to find subgroups of patients. And then that's where Cam asked me, could you do this, have full PHI on the cloud? I said, well, that's not the easiest thing to do, but why not? And then that was this journey where it took us 9 months, because to get the first project HIPAA compliant at Harvard, and it was very interesting because we were already doing it in-house with our servers, but then doing it on the cloud enabled us to have something at the end much more secure and much more scalable to be able to go into a much bigger audience. And so the key point with the HIPAA compliance is that you have to be careful of the PHI, the 18 identifiers that defined by HIPAA as having the name, the address, and all those identifiers for those patients, where once you deal with this data, you have to completely secure your environment to make sure that there wouldn't be any security breach. So one of the first steps to get this HIPAA compliance was to, and with discussion with the security officer at Harvard Medical School and Harvard University, is to look at what are the different security levels in order to, and so that's a policy that was created by Harvard Medical School and Harvard University, of the different institutional review board security levels of data protection. So when I first look at this, I say, hey, let's go for number 5. And then the highest level. But then when I asked they told me, no, you don't want to do this one. Because level 5, there's only one study that was approved as being level 5 in all Harvard University since its creation. It's not my study, and you'll see why, because otherwise I wouldn't be talking here today. So this study is level 5 that wasn't done by me. It was done by another team. It's creating a database of all, and that would be of huge interest for Trump, of all the illegal immigrants in the United States. This database contained a list with all the names of all the illegal immigrants. And so do you imagine this level of security, where if there's a security breach, it's not just the investigator that would go to jail, it's also the participants. So there's only one computer, it's a complete air gap. That's why I wouldn't be talking today. It's not in the cloud. It's a complete air gap. This computer is locked in a room with 2 keys, Faraday cage, in order to be able to do anything. So that's level 5 at Harvard. We managed to get level 4B on going into the public cloud using Amazon Web Service. And so, because of course, I didn't want to have a complete air-gap computer that's useless. I mean, have you seen one? You can't do anything. I mean, you can't do anything with it. And so, in order to get this very high level of security, so that's why it took us 9 months, we had to use AWS-enabled HIPAA compliance tools. And what's very interesting is when we started this journey 4 years ago, there wasn't all those tools available. For example, we were using Oracle. We wanted to use Oracle, so we were using Oracle Enterprise as the backend database. But at the time, Oracle wasn't yet a HIPAA compliant tool with RDS. So we started to do the full installation on protected HIPAA compliant EC2s of the Oracle Enterprise Edition. And the day we've ended it and tested that everything was working, that's where we got the notification that finally, this was in the pipeline that was going to come in the next months. So at the end, we prefer using RDS, HIPAA compliant, than using our own installation on our EC2. But then it's really of looking at what different services are available between the compute, the storage, to make sure that every single system in your pipeline being HIPAA compliant. And so I don't know if you attended this morning the training at the session about the HIPAA compliance, but it's very interesting. As you'll see, there's multiple differences between our approach. And so the first thing is the BAA, Business Associated Agreement. This document, a 6-page document, was signed by Harvard lawyers a year before I even started to be interested in this journey. And so when I heard that there was this BAA, I asked to read it, to have a look. And it's when I read it, these 6 pages, I completely freaked out. I freaked out because I realized so many things that I had to do in order to be compliant. And what's great is the fact that it's the best documentation on how to get started is really to make sure to read this document. Either in your institution, you already have one, or you are in the process of going through, because even, and that's where I was struggling with Harvard lawyers, because they were telling me, why do you even bother? Because you're not a covered entity. You don't have to. But then what we created is to make sure to raise the level of security, even for a public instance, like the enhanced ones I showed you. It's running on a HIPAA-compliant environment, even if it's completely publicly available data. Why? Because we have only one framework in how we deploy to the cloud, how we do installation. And what's interesting is, after doing it at Harvard Medical School, my other employer, Boston Children's Hospital, asked me, why didn't you do it at Boston Children's Hospital, which is a hospital that is a covered entity, and it had to be HIPAA compliant. So what's great is we learned how to do it at Harvard, and then we transferred, and it was a much quicker pathway to do it at Boston Children's Hospital to do it again. With, of course, different accounts, but the method was there. It's really of the thing. And when I told you I freaked out only the day when I read it. And then, because what was very important is the fact that there's so many things that you have to do, but it's well described of what you have to do. And one of the key points is the monitoring. You have to monitor, and this is your responsibility. You have to monitor everything that is going on within the Amazon infrastructure, and you have to save those logs. So there wasn't all those tools available with Amazon 4 years ago. Now there's plenty of them. And so included in Amazon. And what we created is to have one of the most important element is to build our infrastructure as code, to make sure that we don't have any manual process in deploying one of our new stack. So we have in GitHub the code of our various applications, and I only showed you one of them, the user interface, but we have many of them. So the code is, of course, in GitHub, but we also have the underlying infrastructure of how we create, how we deploy the EC2s, the database. Everything is as code using Ansible and CloudFormation scripts so that there's no manual steps. It's just a click of a button to launch the system and then to go and deploy the infrastructure. Because this script was audited to make sure that all the security ports, all the creation of the virtual private cloud, all the different policies that are put in place, everything is well described. And so if someone change anything from the default, then I automatically raise an alarm and I get an email saying, hey, something was changed. So the key point is to have your infrastructure as code to make sure that you truly trust how to deploy it. And within the, for example, the I2B2 Transmart tool, there's more than 45 passwords, system administration password in order between the different database, all the different systems. Every time, so to create randomly this password and how to store it, we use a password management tool called Vault, because at the beginning there wasn't the one from Amazon available, and that enables to have one central place where all your keys are stored, because you can't have, of course, any keys in GitHub. That's obvious, but also because we moved to using Docker, and where you have to be very careful of what you store in your images so that you don't have any secret that are being stored. So one of the key points is really to have a password key store, which is total. Everything that I'm showing here is open source, because it's extremely important within your deployment process. And then we also used vendors. So those vendors, how did we pick them? We just tried many of them. We tried more than, there were maybe 20 of them 4 years ago that we tried all of them to see. So there's a huge overlap between them. But what we really wanted to do is, as an academic, I truly believe in open source, but then I have to be very careful when it was related to the security. So those are the only services that I pay or get huge discounts to be able to use and secure our environment, because I wouldn't want, because there's many different open source tools that exist, but you have to do the configuration yourself. It doesn't come as out of the shelf where you can directly secure your environment and start straight away. So that's where I was willing to pay, and this is the only services that I pay, to be able to completely lock down and secured with overlapping services. But across all of them, I have our application. So for example, from Cloud Checker, we receive every day at 6 p.m. everything that happened in the past 24 hours on the account. With Splunk, we receive every day at 6 a.m. everything that happened across all the different logs of the infrastructure every day of what happened in the past hour. So that's why all the team receive all those mails to check what is going on, to make sure that of what's happening, because otherwise, of course, we have also additional alerts and triggers and alarms that come when something changes, like opening a security port or something like this, but you still need to make sure the number of API calls to your system, because if you have a huge jump, if you have new users that were unexpected in the system, so that's why you have to monitor what is really going on, and then to store, and this for many, many years, if one day you discover that you had a breach. And one also of the key points is to make sure that you have the authentication separated from the authorization. Authentication meaning who you are, and authorization across all your different platforms, knowing what you are allowed to do. So in the context of the patient data, where we create a different level of access, where level 1 aggregate data and level 2 patient level data, but it's really a question of making sure that, for example, for the authentication, that you don't use, you don't store any password. You use external providers, identity providers, so that you don't have the burden of storing all those different passwords. For the deployment using the Docker, where we had the issue of how do we deploy the keys at the same time to make sure that there wasn't any issue. So we used a tool by Cloudflare called Red October that enables, like in the movie and in nuclear weapon submarines, where you can't have only one key that have access to the system. You need to have two keys at the same time in order to be able to access the system, so that the Jenkins, for example, deployment environment wouldn't have all the keys, where you need someone else plus Jenkins to be able to deploy the infrastructure. So that was something very important in the context of using Docker. And then, as I mentioned, using different enterprise identity provider to really secure our environment so that you know exactly who someone is, where we prefer avoiding using Google or any public identity provider, to really focus on enterprise identity provider like the NIH Era Commons or different hospitals or the In-Commons Federation tools, to make sure that we know exactly who is everyone on the system. And then, when something very important is when we mention about monitoring everything, is to make sure that every application business activity is monitored. So it's a question, and that's one of the great advantages of using, for example, Splunk, where with the Splunk tool, all the different pipelines from the different logs are already created. So this enables you to very quickly, and using where we started using the IMI Amazon image of Splunk, we were able to get started in less than 2 hours to be able to have and monitor very precisely all the different layers of information of a stack. And so, yes, there's many different tools that exist. Those are the choices we made, but the key is not to remember the name of the tools that I'm presenting. It's more to have the concept where you have to make sure that you monitor all the different layers, and not just the Amazon infrastructure, but also your application on top of it that is running. Because if you don't have detailed logs, and if there's an intrusion and someone has access to the log, you need to have an external system where to make sure that someone won't be able, and only a one-way system, so that someone can't change your logs. And then what we also do is to make sure that we use the O0 Identity Federated Provider API to monitor the user activity, API activity, and the console API activity of knowing who is doing what. And also something that is very important is the fact that you have to encrypt all your data in transit and at rest. But the key point is, how do you start, before going on Amazon, how can you encrypt your data if you're using Amazon keys? So before the first transmit, so you have to encrypt using your own key that you keep in-house. So there's always some manual steps, but those are very important to make sure that you have a truly secured environment. And then, now that we moved all our application into Docker, one of the real challenges is to make sure that we were still keeping our HIPAA compliant because of all the different level of deployment using Docker. We tried using Docker Data Center, but that didn't really work. So we prefer using the enterprise version of Docker without the Docker Data Center to be able to create this modular open source research services. So where you have what I showed you was this I2B Transmart user interface, but then to have this all, and this is used in the context of creating hypotheses to be able to touch the data, but you won't be able to run the full analysis. In order to run a full analysis, that's where we use Jupyter notebooks that enable to do reproducible science, to make sure that you have the detail of how to make sure that you can redo the analysis. When we publish a study, we use, for example, PubMed, where that's where you have the list of all the different publications in medicine. And what we do is to make sure that in the abstract, where we indicate the reproducible use case are there, present in GitHub, so you have the link of the notebook, so someone reading this abstract will know that he will be able to reproduce the analysis directly. So he will say, by looking at the abstract, he will know he will be able to completely reproduce this analysis. And so showing you with the enhanced case study, publicly available data, With the Simon Simplex, it's another cohort with private data, so someone wouldn't be able to have access if they are not already authorized, but doesn't matter. It's more a question of making sure to have all the script to be able to run an analysis if needed and if you are authorized to access this data. And then to finish, in the context of this NIH Data Commons, a huge NIH initiative where we are in charge of looking at the spectrum of all the various APIs across this project. So this is, within this project, is a publicly available resource, and which is available here with tiny URL DCPPC API overview. Using this, thanks for the mouse, you'll be able to see the overview of all the various APIs that are available within this huge consortium to be able to manipulate all the patient data that enable us to create the research environment for tomorrow that will definitely help us to bring together all those different layers of information. So the key point in the context of this precision medicine is to make sure that how to bring all those different layers of data together to be able to find the subgroups of patients. And so that's various links that you can use in order to use the infrastructure that I presented. And the key point is really, if you have any question, please don't hesitate to ask. Yes. I was hoping to get questions during the session. Yes. Yes, because otherwise it won't be recorded.
So you kind of talked a little bit about aggregating the data, and were there any special considerations in aggregating the data for the reporting purposes and the functionality that you demoed of your application?
In what sense? Because can you be more precise? Because
yes.
there's different ways of answering to this question.
So I'm trying to imagine if, did you have disparate data sources compiled into one? So I was wondering if you could talk a little bit about that in the context of the HIPAA compliance, and were there any special considerations because the data sources were disparate?
Yes. So throughout this presentation, I showed you various infrastructure running on maybe 10 different Amazon accounts, and between Harvard Medical School and Boston Children's Hospital, where every single project has its own instance. Because what is deciding at the end, so the answer to your question is it depends, of course, but it depends of what? That's the key point. It depends of what the patient consented. The key point is really, and that's what I say to all the team members, is when they ask me, can I combine this and this? Well, read the consent. Read what the patient signed. If the patient didn't authorize to be able to combine various data sets, then you can't do it. So that's a crucial point where at the end, so we have many different instances, and this really, and the aggregation really depends on what we are allowed to do. So it's not a technical issue. It's more of making sure that we respect the consent, because that's one of the key points. Because, and the tricky part is this consent can change over time. So for example, for one study, the Simon Simplex collection, I can make the link with the EHR data, but only 24 months after that the patient signed the consent. So then 24 months later, I'm not allowed to make the link with the EHR data. So it's not a technical issue. It's more of making sure that this is possible. But then a related question is, how can I, in a HIPAA-compliant environment, how do we store logs where there's potentially HIPAA data? So that was a very challenging question. And this is really using Splunk, where the Splunk infrastructure is the most protected part of our whole environment, because that's where we had to, this by definition shouldn't contain any PHI, but because it has the logs of application that has PHI data, they potentially in error logs could be PHI that would go into the Splunk instance. So that's where we created very secured environment with, and I'm not going to describe how we secured it, but it's really to lock it down as where there's only a handful of people that are authorized to access it in case of, because that's where there's to make sure that there's no security breach.
Thank you.
Hi. Thanks. It's really great. I have a question. So do you use clinical trials? And the second question is, how do you use machine learning and artificial intelligence to build knowledge out of all the data?
Yes. So do we use clinical trials? Yes, definitely, because this is another source of knowledge around the patient. So we use real-world data, prospective cohorts, including clinical trials, definitely, is just yet another source of data that we can use. And then we use many different methods, because having everything into one central place, having all those various databases where we collected everything, the key point is then to use this to be able to do research, and using statistical models and developing machine learning tools, deep learning. And so that's a completely other presentation than the one I presented today of what do we do once we have this. So this is really the part one. How do we put everything together? And then after putting everything together, it's really how do we do research out of it? How do we do science once that everything has been collected? So yes, we use many different research tools, many different algorithms that really depend on what source of data that you have. But once you have all the data into one place, and every time when I mean one place, I mean that we have this research stack that we do per project equal per consent. So when we have one of the underdiagnosis network project, another one for the autism at Boston Children's Hospital, another one for the autism with a national cohort. And so that's why we have more than now around 20 different research projects. And each of them has its own instance, its own database, its own system. And then there's the authorized postdocs that can have access to it, or publicly available investigators, like you could directly have access to the enhanced one, and the free links are completely publicly available, where you can directly access the data and test various tools, and also accessing using our API. Yes?
Since you're a project with many different partners and collaborators, how do you negotiate the fact that different people use different stacks? How do you get people on board to use that specific set of tools?
Because the first reaction is, oh no, yet another stack of tools. Just give me the data. But then when they realize how we created very nice and very open research environment where they can have a very nice user interface to be able to explore the data, but also an API that enables to do patient-level access to the data. So that's something we developed, is the picture API, BD2 in the context of the Big Data to Knowledge NIH project, where we can expose all clinical and genomic data from VCF of interest, so that you don't have to go and pick download the full file. You only go and select the variables of interest for your analysis. And so, so you don't have to download terabytes of data. You go and only select the variant of interest or the clinical variant of interest, because at the end, when you do an analysis, you don't use always everything. Of course, the first reaction is give me everything, But then this has a cost, this takes time. If you can go and just select the variables that you would be interested, this saves time, and that's one of the key points.
So Mike, thanks. So thank you for taking my question. So my question is really around de-identification of patient data.
Yep.
And so do you have any kind of best practices that you follow when it comes to de-identification of both clinical as well as genomic data? And are you aware of any tools out there, especially in the open source arena, that could be used by others as well? Yeah.
So there's no de-identification of genomic data. That's impossible. Because by definition, your genomic data is unique for someone, so you can't. The only way to make it de-identify is not to have patient data, but to aggregate it between multiple patients. For the clinical data, there's no perfect method. So there's many different tools that exist. We use many of them, but what we do is we use them not in parallel, but one after the other. So because none of the methods are perfect, so we use the first one to anonymize clinical notes, and then we use another one that doesn't know that the first one went through to be able to have something even more efficient. And then, because there's always a risk of having being able to see PHI data for investigator, what we consider is if someone has access to the de-identified clinical notes, then he is considered where he's already authorized to see everything. So it's more a question of knowing what the limits are and being very explicit of what you can do and secure the full stack research environment so that it can hold full PHI. And then you do your best to take everything out, but you consider that there's still some data. A full de-identification of a patient one-page clinical notes takes the time of someone reading all of it and then extracting all the words. So today there's no method that works at 100% to do this. So it's more a question of putting together the various elements to enable to go towards this direction.
Thank you.
Thank you. You said there's different consents that patients sign. How do you follow up on those? Must be very time-consuming to read them in the first place, but then you have to follow up to make sure that you take out the patient from the study if the consent expires. Is there a way to follow up on those easily than manually? And I have a second question. When you merge patients from disparate systems, how do you ensure that this patient is with this data and this patient? How do you match the patient across the systems? Do you have an ID that you use? How do you match it? Thanks.
So to your first question related to the consent, so that's where we consider the consent as the most important phenotype we have. So it's not the age, it's not the sex, it's not the date of birth, it's what is the consent. So this is just another phenotype, like blood pressure, of knowing at what date, so it's a complex phenotype, but this is, and we store it next to all the clinical data. So it's just a question of and each consent that is being signed, for example, does this patient want to be recontacted if something is discovered? That's a flag that exists in some consent, but not in all consent. And so it's just a question of storing this information as if it was clinical data, because it's clinical data. To your second question is, yes, there's always, with all the different layers of information, all the different pancakes, every layer has a different identifier, otherwise there's no fun. And so there's different mapping tables that we use and all that, but that's the reality of how the data that is being generated. Because data is generated by funding sources, and so everyone will have a different identifier, but then if you're allowed to make the link, then you just do it and store it somewhere. Okay, so perfect. Thank you very much. And